All right, guys, today we're going to talk about what are called IMFs, intermolecular forces. That's the forces that hold molecules together, obviously, because most of the things we're dealing with, even the smallest samples of matter, you're talking billions, trillions of different molecules. It says we're out of antibiotics. Take a quarter pound of ground beef every 12 hours. You guys get that? It's a lot of, in the raising of livestock, they're using antibiotics. So if you need to get antibiotics, just get some meat. All right, you guys, three states of matter, gas, liquid, solid, and really the biggest difference is, you think about it, in a solid, the molecules are held together a lot more strongly, right? And they're locked into place. And in a liquid, the molecules are still relatively close together, but they're free to move about. And then in the gas phase, the biggest difference is there's a lot of space in between those particles, and therefore you can compress gases. So what can determine whether, what phase of matter something's in? The kinetic energy of the particles, right? You remember kinetic energy is the amount of energy of motion. And you guys can imagine as a substance absorbs heat, the molecules move faster, and then you can go from a solid, it can melt into a liquid and then vaporize into a gas as those molecules are able to overcome the attractive forces between the particles. So that's what we're looking at today. What is holding those molecules, those particles together? So that's what intermolecular force is, IMF. Attractions between molecules are not nearly as strong as the intramolecular attractions that hold compounds together. So intramolecular, what we're saying here is, right, if we were to heat up like hydrogen chloride, the molecules would move faster and then the molecules would separate. You could tend to go from, like, let's say, a liquid to a gas. So that's going to happen much faster than the actual separation of the atoms within the molecules. So what we're saying here is the attraction holding the molecules together is much weaker than the attraction holding the atoms together. And so if we talk about separating the molecules, we're talking a physical change, right? You go from, like, say, a solid to a liquid to a gas. Whereas if you actually separate the atoms within a molecule, you're talking a chemical change, because then it's chemically, the composition is different. Says they are, however, strong enough to control physical properties such as boiling, melting, vapor pressures, viscosities. Okay. So intermolecular forces as a group are referred to as, sometimes you'll hear them as called van der Waals forces. I tend to just say intermolecular forces, but this is named after a guy who worked with those. Okay, so the first type of van der Waals or intermolecular force we want to look at is, well, several we want to look at are dipole-dipole. You guys, that should look familiar to you. That should sound like a polar. When we say polar, that's essentially what dipole is. Di meaning two. Remember, a polar compound has a partial negative end and a partial positive end because of unequal distribution of electrons. There's also a special kind of dipole force, which is called hydrogen bonding, and then there's one that applies to all compounds, London dispersion forces. So here's one that would actually be involved with a mixture, for example. So let's say we had sorry guys, I'll be here in just a sec. This would help explain. So when we say ion dipole, it's just that. We have ions interacting with dipole, we're talking polar compounds. So for example, it's as simple as this, and even if it's a simple example, at least you have something to look at. So here I've got some water and I put salt. You guys know what's going to happen when I put the salt in the water, right? You guys remember the salt, I'll remind you guys, consists of a lattice structure of different charged ions, sodium ions and chloride ions, right? So I put that in the water, and then what happens, as you guys would imagine, it's nothing really all that spectacular, it dissolves. So what's happening is, you have now an ion dipole interaction. You got water molecules, mind you guys, remember, the water molecules, they're polar, they're uneven. You remember how you can tell if they're asymmetrical, there's an unequal distribution. And so what's going to happen is the water molecules, right, you can see the negative end of the water molecules will surround the positive ions in the salt compound, and then the positive ends of the water molecules will surround the negative ions. And so that's what helps stabilize it. And so that would explain, and you guys remember, water is considered our universal solvent, meaning most things will dissolve in water, and that's due to the polarity of water. The polar molecules, either the positive or negative end, will surround the ions. And so these ions are now separated, and that's why generally speaking, I think I added too much salt, so it's a little cloudy, but you wouldn't see the salt. It's still there, but the ions are separated, and that's why we can't see those. Okay, that's ion-dipole interaction. The strength of these forces are what makes it possible for ionic substances to dissolve in polar solvents. So most ionic compounds, but you guys remember we have a solubility chart. Not every ionic compound dissolves in water, but for the most part, many of them do. Okay, here's one that we really want to focus on is a dipole-dipole. So now we're talking about pure, you guys, in that situation, right, we were dealing with really a mixture. Remember, it was an ionic compound and then water, two different things. That was an ion-dipole. But when all the ones we're showing now, they're all going to be in pure substances, okay? So, in a dipole-dipole interaction, molecules that have permanent dipoles are attracted to each other, and you guys can imagine that, right? You have the negative end of one polar molecule is going to be attracted to, I don't like how it's oriented, we'll say the positive end of this polar molecule is attracted to the negative end of an adjacent molecule, and the positive end and the negative end of one is attracted to the positive end of another, and so that's going to make for a stronger interaction between that, and that can help explain why polar compounds are attracted to each other. The positive end of one is attracted to the negative end of the other, and vice versa. And that only is important when the molecules are close enough together where they can experience the attraction. Okay, so you guys, I want you guys to look. You guys, a big part of chemistry is to look at data. So we collect data, and then we try to make sense of that. So here we have different compounds. We have propene, dimethyl ether. I don't know if you guys can see it from there, but here, this is a hydrocarbon, propane. You guys should remember, hydrocarbons are non-polar. Carbons and hydrogen atoms have very similar electronegativities. The electrons are relatively evenly distributed. So it has a certain, what's called a dipole moment. Okay, that just is a measure of how polar it is. And then notice it has a particular boiling point. Then we have dimethyl ether. It looks like propane, but now there's an oxygen in there. And you guys remember, oxygen is a highly electronegative atom. So once you add that, you're going to tend to make your molecule more polar. And we can see that. It has a higher dipole moment. And now look at its boiling point. And then we have methyl chloride. This is a CH3Cl. We've got this, it's a smaller hydrocarbon with a chlorine. And what we'll see is, what we're doing is we go down, we're making our compound, the compound is becoming increasingly more polar. That means the electrons are less and less evenly distributed, meaning it has more of a stronger negative side and a stronger positive side. So what I wanted you guys to notice, you guys say, what notice? What do you guys notice? You guys should notice, the more polar your compound, what do you notice? The higher the boiling point. What that means is, doesn't that indicate the stronger the intermolecular forces holding it together? Because the more polar it is, the more heat energy is necessary, right, to get those molecules to have enough kinetic energy to overcome their attraction. So the more polar, the higher the boiling point. Put that down. Now, you guys, here's something that's going to be new for you guys, called London dispersion forces. A lot of times we'll just call it dispersion forces. This is a force that applies to all substances. So all substances will exhibit London dispersion forces. Remember, the dipole-dipole will only be exhibited between polar molecules, but this is how it happens. Think about a helium atom. You have a helium atom. 1 second, guys. Let's say we have so we have a helium atom, and right, it's got 2 electrons, right? Helium's it's atomic number 2. It's got 2 electrons. Those electrons are moving around. You wouldn't say an atom is polar or nonpolar, right? It's just by itself. But now you guys think about it. The electrons are moving around, and it's got 2 electrons. Wouldn't you guys agree, at any given time, if the electrons are moving around, wouldn't you guys, at some instantaneous point, wouldn't there be a time at which both electrons happen to be on one side of the atom, right? So in a sense, right, you can see it's kind of an uneven distribution. And now look what that'll do. So, right, so now you might say the atom at that point, the atom is more negative on one side where the electrons are spinning more at that point, and more positive on the other side, right? That's what that's saying, partially negative, partially positive. Now, what that can do is induce a dipole in an adjacent. Now think about it. I've got my helium atom here, and let's say the 2 electrons happen to be, like at one instantaneous point, the electrons happen to be on this side of the atom. That would make this side of the atom partially negative. What's that going to do to the electrons in an adjacent helium atom? won't the partial negative here, won't that repel the electrons and cause the electrons in this atom to move to the opposite side, thus making this atom partially positive on this end and then partially negative on that end. So the fact that you guys, all matter consists of atoms, and all atoms have electrons which are moving randomly, that explains why London dispersion forces applies to any and all substances. So that can help explain why nonpolar substances, remember that have even distribution of electrons, they still will have an attraction for each other due to what are called London dispersion forces. This kind of helps explain. If you didn't have London dispersion forces, think about it, guys. What would everything in the universe be? What state of matter would everything be in? Wouldn't everything be a gas? Everything would just be kind of moving around independently of each other if there was no attractive forces holding them together. But London dispersion forces, unifying force, explains it applies to any and all substances. So all substances will exhibit London dispersion forces, but in addition to that, remember, if they're polar molecules, they can exhibit not only that, but dipole, and then there's a few other ones we want to look at. So London dispersion forces are attractions between an instantaneous dipole and an induced dipole. Instantaneous means where the electrons just happen to be on one side, and then that induces or causes a dipole in an adjacent atom. These forces are present in all molecules, whether they are polar or nonpolar. Okay, so now I want to look at some other trends, guys. Okay, check it out. So here we have F2, Cl2, Br2, I2, once again, okay. And as expected, these are nonpolar compounds, right? So we got, just imagine, trying to show. So just imagine F2, right, is a diatomic chlorine, is diatomic bromine, and then they differ by size. You guys can see they get heavier, right? And then notice the boiling points. And then we have noble gases. You guys remember noble gases? Those are monatomic. So these are diatomic, these are monatomic. Okay, and then those are going to get heavier as you go down the periodic table and then the boiling points. So what do we notice here? First of all, you'll notice all of these are nonpolar substances. You guys would know, obviously a diatomic molecule is nonpolar. It's got the same atom, right? Same type of atom. Aren't those going to share electrons evenly? Okay. But nonetheless, what do? They still experience, you guys remember, dispersion forces. London dispersion forces. What are you guys supposed to notice here? What kind of pattern do you guys see? The heavier the molecule, the heavier the element, the higher the boiling point. And what does a higher boiling point indicate? Doesn't that indicate a stronger attractive force? So that is what hopefully you guys notice. The strength of the dispersion forces tends to increase with increased molecular weight. And you guys, why would that be? You guys think about it. The larger the substance, the larger the atoms. When you guys just agreed, the more electrons there are. And the more electrons there are, the more polarizable it is. The more likely that a certain amount of electrons could be on one side of the atom than the other, and thus induce a dipole, and that's going to make for a stronger attraction. Okay. So you guys, when you're talking about nonpolar substances and you want to predict strength of the intermolecular force holding together, you would predict that the ones that are larger are going to have a stronger London forces, as indicated by a higher boiling point. Larger atoms have large electron clouds, which are easier to polarize. Okay, which has a greater effect? Dipole-dipole interactions or dispersion forces? Well, it says if two molecules are of comparable size and shape, then what's going to dominate is the dipole-dipole interaction. So what you would predict is that the ones that are more polar are going to have a stronger attraction between each other, because, right, you have the negative end of one molecule has a strong attraction for the positive end of an adjacent molecule. Okay. However, if one molecule is much larger than the other, like a lot heavier, more heavier, then dispersion forces might have a stronger effect on it. So, okay, so let's look at a kind of an anomaly here. So this should kind of make sense here. Look at this blue line. I don't know if you guys can see it. CH4, SiH4, GH4, SNH4. Okay, and here it's increasing in molecular weight. All right, and you guys will see here. This is the boiling point, and as we would expect, as the compound gets larger, and these are all, by the way, here's what they are. They're all, you guys see CH4, they're all tetrahedral, CH4, and then what we do is replace the carbon with a silicon, which is in the same column, and then we can replace that with germanium. The only difference is the size of the center atom, but they're all nonpolar, and we see as the compound gets larger, heavier, the Remember, the greater the London dispersion force is holding together, and thus that's indicated by a higher boiling point. So the blue line should look pretty like we would expect. Now on the red line, that's where we see kind of a deviation here. So here, you guys, we have, for example, H2S. So we have 2 hydrogens and then sulfur. And then we have H2Se, and then we replace the sulfur with selenium. If you guys look on your periodic table, hopefully you guys have a periodic table. I know it's kind of hard for me to go back and forth. And then we replace it with tellurium. So in each case, the center atom's getting heavier, and so if it gets heavier, now we have a lot more electrons. It's a lot more polarizable. It's going to make for a stronger force of attraction, right? So it's going up and up. But what we see here is, obviously, here's the anomaly. Here we have water. So what if we had, instead of sulfur in the center, we have oxygen, which is a smaller atom, has less electrons? Wouldn't we expect water, which is the lightest of all 4 of those, wouldn't we expect it to have a lower boiling point based upon using the same reasoning we did on the previous one? However, what we find is water, and you guys should already know this, has a much higher boiling point than any of the heavier complementary compounds. In fact, you guys, we already know water has a boiling point of 100 degrees Celsius. So the question is, what would cause water molecules to have such a strong attraction between them? And I think some of you guys might remember from last year. Okay, so we're pointing out the anomaly of water. And they're saying that the nonpolar ones follow the expected trend, but then we have this one here. The anomaly is water. What might explain this? And here it is. You guys, we have dipole-dipole. First of all, you should know there were dipole-dipole interactions, right? You guys know, look, in this kind of molecule, you remember how you can tell it's a polar compound? You remember if it looks asymmetrical. So there's an uneven distribution. And also, if you have like lone pairs of electrons on the center atom, it's usually going to be a polar. So what's going to hold molecules like that together? When we say dipole-dipole, right? You guys were right. The partial negative end of one molecule is going to be attracted to the partial positive end of another molecule. Okay. So we've got that, but we still have to explain why did water not fit the pattern. We would still expect the larger the molecule, the stronger the intermolecular force, but water is much smaller, yet it has a much higher intermolecular force. So, and it's what they find is whenever you have hydrogen bound to an exceptionally electronegative atom, and it has to be either nitrogen, oxygen, or fluorine, that's going to make for an exceptionally strong intermolecular force. So look at water molecules here, and here's the reason. You think about it, guys, and water is a good example. So we have a very highly electronegative atom like oxygen, nitrogen, or fluorine. In case if it's water, it's oxygen, right? And then we have hydrogen. You guys got to remember from the periodic table, hydrogen is your most simplest atom. It contains a proton and an electron. Well, we already know there's a covalent bond between the oxygen and the hydrogen, right? Between the two nonmetals. So hydrogen's one electron, it's being shared between the oxygen and hydrogen. And not only that, because this is very highly electronegative, that means that those pair of electrons are orbiting the oxygen atom with much more frequency. So essentially, what does that leave here? What's the only thing? A hydrogen atom only consists of a proton and electron. If it's one electron spending most of its time orbiting the oxygen, what's left here? Essentially just a proton. So this kind of situation has exposed a proton. It's essentially like a naked proton. So you can imagine that has a very strong attractive force, you can imagine, for the partial negative end of an adjacent molecule, making for a much stronger intermolecular force between these than we would otherwise expect. And that's what you guys are going to have when you have nitrogen, oxygen, or fluorine directly bound to a hydrogen. So that can happen in water, we talked about. It can happen in NH3, right? That fits the scenario as well. We call those hydrogen bonds. That's what you guys probably remember from last year, hydrogen bonds. That's an extra strong dipole-dipole interaction. Okay, and it involves, apart from the high electronegativity, nitrogen, oxygen, and fluorine. So when hydrogen is bonded to one of these very electronegative elements, the hydrogen nucleus is exposed. That's what we're saying, essentially like a naked proton. Okay, so you guys, here's another type of interaction. We have we have covalent network and molecular solids. You guys have noticed both of these are referred to, whenever we refer to molecules, we're talking about nonmetals, and then the covalent, we're thinking of nonmetals as well. So here's diamonds is a perfect example of a covalent network. Okay, so put that, diamonds. You guys know what diamonds are. You guys know that it's just carbon atoms. So you guys see why it's called a covalent network. It's kind of like this. You guys remember our lattice structure, metals and nonmetals, remember like salt? Well, it's kind of like, just imagine nonmetals sitting in this network. That's essentially what a covalent network is. So in diamond, for example, you have the carbon atoms sitting there, and you have each carbon atom interacting with, it looks like in this case, maybe 5, 6, 7, or 8 carbon atoms surrounding it, and that's going to actually make for a very strong bond. In fact, we can see that, and we know that from what experimental evidence, the fact that diamonds, for example, have a very high melting point, very hard. You guys know they're one of the hardest substances. In fact, we can use like diamond tip blades on like chainsaws and things like that, on saws, because it can help cut other things. So that would be an example. So just think diamond is an example of a covalent network solid. And then another type would be graphite. And this is what's kind of interesting, because you guys know when we say graphite, right, that's the end of your pencil. And you guys, just like diamonds, that's also made of carbon. But obviously that has distinctly different properties, the graphite on a pencil, than diamond does, right? When you guys are writing. And here, if you look at how they're arranged, the carbon atoms look, right, they have this kind of intricate pattern, but you'll notice that they're kind of in layers. So there's a very weak interaction between these layers. In fact, that's why we can use graphite for pencils, right? When you guys are writing, I talked about this before, when you guys write with a pencil, what are you guys doing? You're just leaving layers of carbon atoms on your paper. That's what you're doing, as layers are sloughed off, just via the friction as you move your pencil. So, as you might imagine, in this kind of, so you guys can see it gets kind of complicated, because in both cases they're both carbon atoms, but how they're bond to each other, and you guys, right, and that's just based on the conditions in which you find them. You guys know diamonds are produced over hundreds of years with a lot of pressure and temperature, and that's what creates this very intricate network here. But then graphite, under different conditions, are going to produce layers of carbon atoms. And that would be an example of a molecular solid. Okay, last one, metallic solids. You guys here, I think I showed this before. Think about the positive is like the nucleus of your metals, right? You guys got your metal. I mean, what kind of metal we got? We have metal. Well, okay, I got a paper clip. So, right, that consists of billions of, probably iron and some other metals, maybe some stainless steel if this doesn't rust. And so, think about the metal atoms and the core electrons. Remember, what are we always interested in? The valence electrons. That's what the negative signs are indicating. And what this picture is trying to show us is that those valence electrons are not localized around individual atoms, but those valence electrons are kind of free to move between adjacent metal atoms, which helps explain the high electrical conductivity of metals as well. Okay, metal valence electrons are delocalized throughout the solid and thus not tightly held. All right, guys, got a little bit more here. This is kind of a long one. What metallic property might this explain? We talked about that, electroconductivity. He says, that's one of mine. Feel free to repost and share. So he kind of left his little doggy message there, and this one can respond back. All right. Guys, a few extra terms for you guys. We got heat of fusion and heat of vaporization. So we're showing here, well, we want to introduce, here we have butane, diethyl ether, water, and mercury. And so in the purple, what that's showing is the heat of fusion. And that's the heat of fusion is the energy required to melt a solid. And you guys can see this is in kilojoules per mole. So for example, for water, what it would say is the heat of fusion is 6. That means it takes 6 kilojoules of heat to melt. If we had a mole of water, which would be 18 grams of water, it would take, ice, let's say ice, it would take 6 kilojoules of heat energy, just imagine ice locked into place, to melt that to become a liquid, okay? So that's how much heat it would require. That's called the heat of fusion. And you guys, it shouldn't be surprising that you guys look at butane, C4H10, it's a hydrocarbon. Remember, that's non-polar. Remember, the forces that hold those together are just dispersion forces. Those are kind of weak. And so it's not surprising it only takes 5 kilojoules to separate that out. It takes less energy than it would water, and then you compare it with mercury, which is kind of showing you how strongly these atoms or molecules are held together. Now that was just the purple. Now this whole thing is showing us both heat of fusion and heat of vaporization. Heat of vaporization, that's the blue. That's the energy necessary to change a liquid to a gas. And guys see I have a what notice. So you guys like compare the heat of vaporization with the heat of fusion for each of these substances. And what do you guys notice? Which is much higher? Like let's just focus on water. This can kind of get kind of confusing if you look at everything at once. Don't you guys realize the heat of vaporization for water is 41? It takes 41 kilojoules of heat to completely vaporize 1 mole of liquid water, whereas it only takes 6 kilojoules of heat to melt 1 mole of ice. So it's like 7 times more energy is necessary to vaporize it than it was to melt it. So what does that tell you? What might explain that? So once again, just imagine they're locked into place. The heat of fusion for water is 6 kilojoules per mole, so it takes 6 kilojoules of heat, just imagine I'm heating it up, to get it to, and what you're doing is you have to overcome the attractive forces between it. But now, look, it takes 41 kilojoules, so just imagine liquid water. Okay, we've got some water, just imagine water, okay, imagine the molecules there. So then I would imagine I had 1 mole of water, that would be close to this, probably a little bit more than this. And it would take 41 kilojoules of heat to get that to completely vaporize. Why does it require so much more heat? Because you guys think about it. When you're vaporizing it from a liquid to a gas, what are you doing? You are completely separating out the molecules. You are completely overcoming the intermolecular forces holding it together. And that explains why it requires so much more energy to vaporize a substance than it did to just melt a substance, because you're not necessarily overcoming the molecular forces, intermolecular forces, when you melt it in the heat of fusion, but you are when you finally vaporize it. All right. So it says, what explains why temperature does not rise at certain points? Oh, so guys, this is called like the heat curve for water. Like just imagine if we had, so just imagine we have water at negative 25 degrees Celsius. When you guys agree at negative 25 degrees Celsius, your water is ice, right? The molecules are locked into place. I should do like this, right? It's because it's the partial negative with the partial positive. So then, let's say I apply heat to it, and what's going to happen is, in that ice, you apply heat to it, you'll notice like the temperature's on the y-axis, the temperature will rise. That makes sense, right? As it absorbs heat, the temperature rises. When we say the temperature rises, what are we saying? You guys remember temperature is a measure of the average kinetic energy. Kinetic energy is going up. But, you guys, what happens is, it's still what though? It's still ice until what point? Until you reach 0 degrees. You guys know that's when ice melts. That's the melting point of water, 0 degrees. Then you guys will notice as you're applying heat, so then it begins to it's melting. It becomes to get released from the fixed framework it was in, and now just imagine liquid water. And you'll notice even as you're applying heat though, it's kind of interesting. If you had a temperature in there, if you had a thermometer in here while that's happening, what would you notice? The temperature is not changing. So in this case, when it's absorbing all that heat energy, it's not being used to increase the kinetic energy of the molecules. That's just being used, that energy is being used to overcome the fixed, attraction between the molecules, okay? And then, once all your ice is melted and you're continuing to apply heat, what begins to happen again, obviously, the temperature begins to rise, and just keep rising, and you can just imagine the molecules are just moving faster and faster and faster, because that's what's happening when the temperature is rising, until you hit 100 degrees Celsius. Then at 100 degrees Celsius, you guys know this, 100 degrees Celsius is a boiling point of water. That's when the water molecules begin to boil or vaporize. And even though I'm applying a lot of heat energy to there, notice the temperature is not going up, because all that energy is being used not to speed up the molecules at this point, but to overcome the intermolecular forces holding it together. And so it'll stay at 100 degrees until all of your water has been vaporized. Then the temperature can shoot up, and you can get kind of like infinitesimally high water temperatures. That's why you guys got to be careful more about steam than you even do with boiling water. He added the system at the melting and boiling point goes into pulling the molecules apart from each other. Okay, and it's saying the temperature of the substance does not rise during the phase. So you guys see this? You guys notice, check this out. You guys see how small this is? Remember, it's the heat of fusion. Remember, it doesn't require as much energy. And then you notice this requires a lot more time. Basically, it's absorbing a lot more energy in order to fully vaporize. That's the heat of vaporization. Oh, all right, guys, I think we're done now. Thanks for sticking with me. We'll see you guys next time.